This video is going to show you how to calculate percent dissociation, and we're going to use hydrogen fluoride. We did an earlier problem where we used, I don't want that, we used a 1 molar solution of hydrogen fluoride, sorry about that, and we got 2.7 times 10 to the negative 2 as our hydronium ion concentration. I want to use that as a comparison. So 2.7, this was if we had a 1 molar solution of HF. Our hydrogen ion concentration was 2.7 times 10 to the negative, I think maybe it was second, not fourth. Nope, it was second. Sorry about that. Okay. So that was with 1 molar. Now we want to look at 0.1 and we're going to look at 0.010. So I'm going to go through this part really quite quickly. Hydrogen fluoride, I look at that. I know it's an acid. I ask myself strong or weak. It's weak. So I know I have to write a reaction. I have to do an ice table. So hydrogen fluoride plus water. Actually, let me show you how to do it without doing it that way. It'll be different. So that's going to dissociate into hydrogen ions and fluoride ions. Initial change, equilibrium. I want to put in my 0.10. Both of these are 0. I don't know, because I don't have equilibrium concentrations, how these are going to change, so I'm going to use X. Hydrogen fluoride goes down by X. Hydrogen ion and fluoride ion go up by X. 0.1 minus X, X, and X. Now, just as a comparison, I'm going to do B here. So I'm going to write the same reaction again because it's the same substance. I'm going to create my initial change final table. And then I am going to include my 0.010 molar solution. Hydrogen ion and fluoride ion are both 0. Don't know how much this is going to go down by because there's no equilibrium concentrations. So I make my change minus X, and then I end up with my equilibrium concentrations. Now, earlier we wrote the expression for hydrogen fluoride, and I don't want to do that right now because we've done that before. So I'm going to substitute directly into the equation. So the Ka is 7.2 times 10 to the negative 4th for hydrogen fluoride. I'm going to do that equals X squared because X times X. I'm also going to approximate because if I take the Ka of hydrogen fluoride and I multiply it by 100, in both cases it is less than or equal to the initial concentration, so that we know that X is going to be very small in comparison. So I'm approximating in both situations. So I'm going to go ahead and very quickly solve each. Okay, so the first one, 0.1 times 7.2 times 10 to the negative 4th. Take the square root of that quantity. I get 0.0085 molar. That is our concentration of both fluoride and the hydrogen ion concentration. But all I'm really concerned about right here is hydrogen ion concentration. Okay, I'm going to do the same math for the second example. So 7.2 times 10 to the negative 4th times 0.010. I'm going to take the square root of that quantity, and I am going to get 0.002683 molar, which tells me the hydrogen ion concentration over here. Now, if you look at those two values, you ought to notice that the one on the right is slightly smaller, which should make sense because you have an initial concentration that is smaller than the one on the left. Okay, I just decided that my math on the left does not look right, so I am going back and I am checking it just to be sure. Nope, my math is on over here is okay, so that's fine. All right, I'm not asked to calculate pH. If I were, I would just do negative log of these values, but I'm not. So I'm just going to do percent dissociation. So to get that, our percent dissociation is going to be the hydrogen or hydronium ion concentration divided by the initial acid concentration. And then that's going to be times 100. So in this instance, it's 0.0085, because that's our hydrogen ion concentration, divided by 0.10 times 100. So when I do that, I get 8.5% dissociated. When I do the same thing with the second one, let's change colors. Guess let's do yellow. So 0.00268. That's good enough. This is going to be percent dissociation divided by our initial concentration, 0.010 times 100. So that will be 0.00268 divided by 0.010 times 100 gives us 26.8% dissociated. All right, got to check my math. Okay, on this top one up here, I did, where's my pen? This was my hydrogen ion concentration. I'm going to divide that by an initial concentration of 1 times 100. So we got 2.7% dissociated or ionized for this first one. Okay, so what we want to do is we want to look at these values and see what they mean, because there's definitely a trend. The more concentrated, the less dissociated it is. So we want to think about this in terms of Le Chatelier's principle. So what's happening is the concentration of, in general, as the concentration of the weak, whoops, sorry, I didn't mean to move that. As the concentration of the weak acid decreases, so from here to here to here, you're going to see that the percent dissociation is going to increase. And we can talk about that in class if you have a question.